Welcome to Hydrogeology 101 pumping tests. Today I'd like to talk about the Cooper-Jacobs straight line method for the analysis of non-steady state pumping tests in confined aquifers. Quite a mouthful. Let's just call it the straight line method. In a previous video we talked about the TICE method, where we plot drawdown along the y-axis and time along the x-axis, all on log-log paper, and then we plot our TICE curve through the data as shown here. Now, if we take this same data and we plot it on semi-log paper, like so, where drawdown is on the normal scale and time is still on the log scale, you'll notice that these data points, the early data points, they start to curve slowly towards what appears to be a straight line. In fact, we can draw a straight line right through it like this. And you can see that all the late data points appear to plot on a straight line. Now this is the fundamental principle of the Cooper-Jacobs method, which is basically a simplification of the TICE method. The Cooper-Jacobs equation is based on the TICE equation shown here. Just to remind you, S is the drawdown at any distance r from the pumping well at any point in time t after the beginning of the pumping tests. And the important thing is our well function here, where u equals r squared, the distance, times by the storativity divided by 4 times the transmissivity times by time. Now what Cooper-Jacobs said was that if the distance r, that means the distance from our pumping well, is very small, then u will become small. And the same is true for t. When t becomes very large, we're dividing by a large number here, then u will also become very small. If u is sufficiently small, then we can simplify the TICE equation. Basically, we can neglect all this part of the equation. Now, what happens when u is not very, very small? What happens when u is, for example, 0.03? Well, then our error is only 1%. This comes from Kruzman and de Ruyter, by the way. And you can see that at higher values of u, for example 0.15, we'd have an error of 10%. Now most hydrogeologists agree that an error of 2% is quite acceptable. So what we do is, if u is less than 0.05, then we can use the Cooper-Jacobs method. Okay, so the way it works is we just delete this part of the TICE equation. So we rewrite it like this, and if we merge this equation with the one for u, we come up with the Cooper-Jacobs 1946 equation in natural logarithms and also in log to the base 10. And just to remind you about the parameters, what's really important is that we remain consistent. So for example, the drawdown has to be in meters, discharge meters cubed per day, transmissivity meters squared per day, the distance r in meters, and of course time in days. Another key thing that we need to consider is that this equation only works when u is small, when it's less than 0.05. So after you've calculated transmissivity and storativity, you need to plug it into this equation to see if it still conforms to the Cooper-Jacobs assumptions of a very low u. Okay, so there are two methods for which we can use the Cooper-Jacobs method. One is time drawdown and one is distance drawdown. Here we have a pumping well pumping at a rate q, and you see that over time the cone of depression propagates both downwards and outwards. If we have an observation well at a fixed distance from our pumping well and we record the drawdown at various points in time, we can plot it like so. So the drawdown on the y-axis, time on the x-axis, and then you'll see that as time progresses, drawdown increases. Basically, it's going down. This is what's called the time drawdown method. If we pick a certain point in time and we measure the drawdown at various distances from our pumping well, then we can plot it like this, and you'll see that the drawdown will decrease as we get away from our pumping well. And this is called the distance drawdown method. Okay, let's illustrate it with an example from Kruzman and Derrida, the Ode-Korendijk pumping test. We had a pumping well here which was pumping at about 800 cubic meters per day, and there are 3 observation wells at 30 meters, at 90 meters, and at 215 meters. Okay, let's start with the time drawdown method. Here is the data for the piezometer at 30 meters from the pumping well, and we have drawdown on our y-axis and time on our x-axis, and you'll see that the early data starts to curve downwards and then it starts to fall onto a straight line. The late data is diverging from the straight line, probably because of some leakage effects. Okay, so what we need to do is just put a straight line through the data here and find out what is the change in drawdown, delta S, over 1 log cycle. So that means the difference in drawdown at the start of a log cycle and at the end. This delta S will also be the same if we measure it here, for example, between 1 and 10 minutes. The delta S is what we need to calculate transmissivity using this equation here. If we extend our straight line to the point where drawdown is 0, we have a time value which is t0. In this case it's 0.25 minutes, and we need t0 in order to calculate the storativity using this equation here. Okay, so now if we plug our numbers into the equation, we see that transmissivity is about 387 meters squared per day. And the next thing is to calculate storativity, where we actually need to take this transmissivity number and plug it into the equation here. So we cannot calculate storativity before we calculate transmissivity. Also, please notice that T0 is actually in minutes, so we have to divide it by 1440 to get it all into consistent units, i.e. days. We have a storativity of 2 times 10 to the minus 4, so we can say that it is a confined aquifer. Okay, let's have a look at the distance drawdown method. As I mentioned before, we have 3 piezometers at 30, 90 and 215 meters, but actually in this example where we are looking at the drawdown after 140 minutes, they don't all plot on a straight line. And the reason for this is that in this furthest away piezometer, U is probably still too high, so it doesn't apply to use the Cooper-Jacob method for this observation well. Anyway, let's have a look what we can do. We can have a look at the change in drawdown over 1 log cycle and use that to calculate the transmissivity. And we can also find out what is R0. That means the edge of the cone of depression where the drawdown will be 0. It's about 450 meters. And that is then used to calculate storativity. As with the time drawdown method, we need to calculate the transmissivity first and then plug it into the equation for storativity. And we get 4 times 10 to the minus 4 and 370, which is a little bit less than what we got for the time drawdown method. Now, we only have 2 data points for this distance drawdown method, which is not very good, so it's better if we use the data from the time drawdown method to calculate our aquifer parameters. 387 meters squared per day, we can round that up to 390, and we'll use a storativity of 2 times 10 to the minus 4. This is a quick summary of all the equations for the Cooper-Jacob method. Just please remember that U must be less than 0.05 or we cannot apply the equations. Okay, let's have a look at the Excel spreadsheet called Cooper-Jacob Excel, which I developed in Ghana back in 2003. In the info datasheet, there are a whole bunch of instructions telling you how the spreadsheet works. In data, what you need to do is add all of your time and water level data, discharge data and conductivity if you have it, into these green cells here. and there's quite a bit of space, so you can add as many as you want. And then you need to add other important information up here. So this is called info1, info1a. So what you can do is you can add any information here which you like. It doesn't matter what it is. It's quite flexible. One thing that you cannot change is the distance r. You can see it here, distance r, distance to the pumping well, the pumping rate q, and the static water level, which I've called water table. That's this cell here. So these are fixed because they're important for the calculations. Then the rest down here is also just information, so measurement datum, pump on, pump off, who measured it, whatever. So what it means is that apart from these three cells here, you are free to do whatever you want with the information you put in here. You only have to enter it once. It'll later get transferred to our print sheet. What's very important is that here you enter the correct time of your first pumping water level measurement. Okay, and afterwards the time here is calculated automatically from this first cell, and also the time here in minutes of your measurements. The drawdown is calculated from our water level and our static water level. In this case, these water levels are already drawdown, so I've just put in here a static water level of 0, but basically that's not normally the case. After we've plotted it, you can have a quick look at it here on the chart to make sure that the data looks good and it's not doing anything funny. And then all you need to do is go to the analysis sheet. Now this is where we plot our straight line to the data. And in previous versions of Excel, I think up to Excel 2003, you could just grab the end of this red line and pull it up. Unfortunately, it's no longer possible, so we have to use these sliders here, like so. Okay. Now there is a very important cell here called the sensitivity. If we increase the sensitivity, then our line goes upwards. Okay, so our drawdown becomes less, and the sensitivity determines the maximum and minimum that we can slide the slider up and down to. So let's try with, whoops, you'll get used to it after a while. What we want to do is make sure that our line goes through all the data points. So this one here, it ends at 100 minutes, which is not good enough. Let's take it to, let's say 200, 300, let's say 400. So x2 becomes 400, and we can keep that at 1, that's not a problem. As we move this line around, you'll notice that there is this dotted black line, which is shifting around from left to right. Now that is the line where u is 0.05. Okay, so what it means is that to the left of this line, we shouldn't really take these data points very serious. So let's see if we can fit the data. Okay, I think that's pretty good. Okay, so I think we'll stick with that. You see that the early data is curving towards the straight line, and then most of the data points plot on the straight line. We can then look at it here just to make sure that we're happy with our results, and I'm quite happy with the results. You see that here is our line of 0.05, and also the data points change in symbol, so they're squares to the left and circles to the right of our 0.05 U line. If we go to data, you can see here the calculated drawdown, which is based on our Cooper-Jacob straight line equation, and the fitting error in percentage. Now, the points which are above u equals 0.05 are not included in the analysis of our overall error. If we go to print, you can see the error here, the mean fitting error of 0.29%. And all the information which we entered previously in the datasheet is now coming up here automatically. And you can see the transmissivity has been calculated, as has the storativity. If we have a distance to a pumping well is less than about 3 meters, it doesn't calculate the storativity. So it just stops you from calculating the storativity in a pumping well. Okay, now the full version of this tool also will show your conductivity here, but I've deleted it because we don't have that data in TOT. There is a hidden sheet called Calcs, which please don't touch it. It is hidden because if you mess with the calculations, it's going to give us the wrong results. But basically it is there in case you ever find it. So that's it. Then all you do is File, Print, and we can print entire workbook if we like. Yeah. Obviously don't print my instructions, but here is our data sheet, empty cells, and here's our chart. Whoops. Chart, our calculations, our semi-logarithmic plot, and the final plot. So normally I would just give to the client the final plot here and the data sheet, so that we're working in a very transparent way. They can see exactly how we derived our transmissivity and storativity values. Okay, I hope that you found that interesting and informative, and that you enjoyed it as much as I did. And I thank you very much for your attention.